Hi everyone, this video is on Fast-RCNN, our second method in the object detection series. The plan for this video is to first understand the problems with the RCNN approach and then see how the architecture of Fast-RCNN tries to solve these problems. We'll also dive deep into ROI Pooling, one of the main components of Fast-RCNN, and how it's actually implemented in PyTorch. And finally, we'll get into how the entire Fast-RCNN model is trained and the results that we get with it and how it fares in comparison to RCNN. So let's jump right into it. Before getting into Fast-RCNN, we need to get some sense of why is it needed in the first place. So to recap, for our RCNN model, given an image in which we want to detect objects, we first extracted region proposals using off-the-shelf algorithm, specifically selective search. Then each of those proposals were resized and fed to our CNN, which was trained to generate classification scores and bounding box regression values given a resized proposal image. And the way we trained this model was we first trained CNN on the large ImageNet classification dataset, fine-tuned the CNN to classify proposals as background or some foreground class, then trained class-specific SVMs to use the FC layer representation of these proposals and predict if it's a positive instance of that class or negative instance. And as the last step, we also trained bounding box regressors to take the pooling layer representation of proposals and modify the proposal boxes to get a better localized box for the object of interest. If you need to review what's happening in RCNN in detail, do check out my video on it before going ahead with Fast-RCNN. The authors of Fast-RCNN mention the following problems with this approach of object detection. The first is to do with how training RCNN requires training 3 stages, and rather than single training task, one needs to manage the entire pipeline of 3 sequential training tasks. The second problem is that since the SVM is trained on FC layer representation of training proposals, we first need to compute this representation for our entire training dataset of proposals, which not only has a time cost, because we'll be doing a forward pass for all proposals for all images, but it also has a disk space cost attached to it. Since there are about 2K proposals per image, just few thousand images means a requirement of a lot of GBs of storage. Now these two problems are still just with training. But even if we are okay in digesting a one-time training and disk space cost and managing the pipeline, we have to also live with the slow inference time for detecting objects. Since for detection, we basically do a forward pass to the model for each of those proposal regions. So 2K forward passes, which roughly takes about 47 seconds for an image. This number is obviously with a very old GPU, but still, the fact that so many forward passes are required will remain true no matter what. Let's first try to see how the authors deal with the last problem, that is making object detection faster. So we know that the root cause is that we are doing forward passes through the CNN for all the proposals given an image. And we need that because we need to get feature representations for each proposal for the later prediction layers. With the goal of trying to reduce this cost, given an image and say these region proposals, rather than feeding each of them separately, we could pass the entire image to CNN. And then from the last feature map, we could use the coordinates of the proposal with respect to image and the scaling factor between the image and the feature map to identify the coordinates of the proposal in this generated feature map. And then extract the feature representation of these proposals from these feature maps. And then flatten them and feed it to FC layers for whatever predictions we need, be it the fine-tuning classification stage or the SVM or the bounding box regression stage. Hence, rather than doing as many forward passes through CNN as there are proposals, we are only doing one pass through conv layers, and only the FC layers are executed for each proposal, which we really cannot get away with because we need predictions for each proposals. But unfortunately, we can't follow this exact approach. This is because these proposals will be of varying size, and hence their corresponding feature map crops will also be of varying size, and simply flattening them will lead to different dimensional vectors, but the FC layer is expecting fixed dimensional input for all proposals. To tackle this, the authors introduced something called ROI Pooling layer or Region of Interest Pooling layer. And the responsibility of this layer is to take these proposal regions and extract a uniform output size from the convolutional feature map, no matter what the shape of input proposal region is. That way, after ROI pooling, we can flatten the output for all proposals to the same dimension and then feed them through FC layers. Let's look closely inside these pooling layers. Assume our desired uniform output size is 2 x 2 as an example. Then the ROI pooling layer will essentially divide the feature map corresponding to the proposal coordinates into 4 regions. Then perform max pooling within each of those regions to generate the 4 values of this 2 x 2 output. Though essentially that is indeed all that happens within the ROI pooling layer, but there are a few details that we need to look at. Say this image is a 400 x 400 image, and assume the CNN downscaling factor is 40 rather than typical values of 16 or 32, just to make the math simpler. So our final feature map would be 10 x 10. Now if we try to find the exact location of this proposal using coordinates in the image, we end up getting this region in the output feature map. The problem is that this corresponds to non-integer coordinates. In fact, that will be the case whenever we have any proposal which has a coordinate in the image that is not a multiple of 40. In order to extract feature map regions for such cases, we always quantize the location of proposal in the feature map by rounding. Do note that what this would do is get rid of some regions which were inside the proposal box, like these two, and it would also be adding these regions which were previously outside the proposal box. In a later method, we'll see how to take features of proposals without quantizing, but for now we have to live with this. Okay, so after this, we can get the proposal features by dividing into regions. But dividing into 4 regions is also something that's not trivial. Like here, our output feature map for this proposal is 8 x 7. So dividing across the width is easy, but how do you divide across the height? Like this or this? And you could also allow overlaps. Then the 4 regions could be these, or even these. How we choose to divide is an implementation detail, but post that we just do max pooling within each of those regions to ultimately get our 2 x 2 output. And here I use 2 x 2 as an example, but the pooling layer output can be any W x H, as it need not be a square. The actual implementation of pooling for Fast-RCNN is borrowed from another paper in which the authors use floor and ceiling operations to figure out what all locations of input feature map need to be considered for max pooling given an I x j cell of output unit, and then pool over values at these locations. And this process is repeated for all I x j. Let's look at the PyTorch code to kind of get better sense of how exactly this is implemented. So assume this is the proposal feature map of ROI width and height, and this is after quantization. And our desired output shape is of pool_w and pool_h dimension. The first thing we do is get the bin size across height and width, which is just ROI height and width divided by pooling height and pooling width. Now we iterate over all the output locations, and for location I, j, we get the starting and ending locations across width and height. These will give us the set of values over which we would max pool. To get the starting location along y-axis, we do floor of j times bin size across height, which is same as ROI height divided by pool height. And the last location for y-axis is ceiling of j+1 times the bin size across height. The same kind of formulation is also used along x-axis. Once we have computed the starting and ending locations, we simply fetch the values corresponding to this region and do max operation within those values. And this entire process is repeated for all I, j values. Let's try to visualize over what values this max pooling happens for sample proposal sizes. So here we are going to see a 4x4 and 5x5 proposal feature map, and over what values max pooling happens during ROI pooling. And the ROI output size is going to be 3x3. The last row indicates which value in the output unit is being computed, and the first row's green box indicates over what values max pooling happens for this output location when the feature map is 4x4. And the second row indicates the same, but when the feature map is 5x5. Again, this way of dividing regions is just one of the many different possible ways of implementation. And since I just wanted to give a bit of detail on how the PyTorch framework implements this, hence I used the PyTorch ROI pooling implementation. Just to reiterate, rather than directly using the extracted features from the feature map, we first have a ROI pooling layer which ensures that all the different proposals are mapped to a uniform output shape, which can then be flattened and passed to FC layers for predictions for later stages. This entire ROI pooling was just to ensure that we do one forward pass for all proposals of an image, which in turn was to improve the object detection speed. But that was only one of the three problems with RCNN. Let's see what the authors do for handling the other two problems of multi-stage training and disk space cost for SVM training. For this, rather than having 3 stages of training as in RCNN, the authors of Fast-RCNN take the flattened ROI pooling output, feed it to a few common FC layers, and then have 2 branches of FC layers. One of them responsible for predicting the class probabilities for the proposal for the K+1 classes including background. And the other is the bounding box regressor, which predicts 4K values, which are the 4 regression values for the K classes. The bounding box regressor is the same as RCNN that we have seen, no change at all. The proposal box coordinates and the ground truth box this proposal is assigned to is used to get the transformation parameters Tx, Ty, Tw and Th. These become the label for the 4 values of the bounding box regressor belonging to the ground truth class K that this green box had. And then, just like RCNN during inference, given a proposal with a foreground class prediction, we fetch the transformation parameters prediction from this bounding box regressor and use the same transformation to find the new box location. Now we have seen all the parts of Fast-RCNN model. So now let's look at all of them together and see how it's trained for detection. In RCNN, we were using ImageNet pre-trained classification models and fine-tuning them for detection. But now our architecture has this new ROI pooling layer. So before actually training, rather fine-tuning for detection, let's see how the authors initialize a Fast-RCNN model from a pre-trained image classification model. Typically, the pre-trained models will have a conv activation layer at the starting, and there will be multiple such layers. Then max pooling will be used to downsample the input, and this entire stack of conv activation max pooling will be repeated. Finally, we'll flatten the input and have some FC layers, and the final FC layer will have the same output units as there are classes with softmax. For ImageNet, it will be 1000 classes. And given an image, we'll get the probabilities from this final classification FC layer. For using a pre-trained classification model, the authors replace the final FC layer with 2 branches of detection: classification and localization, just like we saw earlier. Now comes the ROI pooling part. What the authors do is they remove the last max pooling layer and instead add a ROI pooling layer with the same output size as that of the max pooling layer. So if the max pooling layer output was 7x7 with 512 channels, then it would be replaced with the ROI layer of 7x7 output size. Since both max pooling and ROI pooling do not change the channel dimensions, that means after flattening the ROI pooled output for any proposal, we'll get the same output size that this pre-trained FC layer expects. The input to the network is now an image and a list of proposal regions. The conv layers are same as the pre-trained weights, and again for an image, these will be called only once to generate the feature map. The ROI layer will use the proposal region inputs, and for each of the proposals, it will generate same sized output. We'll pass these to the FC layers, which again are pre-trained, and the ROI pooling ensures that the shape is same as what these pre-trained FC layers expect. And post that, we have the randomly initialized classification and bounding box FC layer. Let's now get into fine-tuning for detection. During RCNN, for fine-tuning of CNN, we randomly sampled background proposals and proposals with some foreground class label from the entire training dataset. But think about the case of the same image and these proposals. If both these proposals belong to different batches, then for this batch, we would forward pass the entire image, get the feature map, and ROI pooling to get proposal features. Then again for this batch, we would do the same to get the proposal features using ROI pooling. So the computations in these layers is exactly the same. Image to feature map computation is happening twice. But if these were in the same batch, then this computation could be shared, and that would make the training more efficient. To achieve this computation sharing, the authors modify how the proposals are sampled. In Fast-RCNN, we first sample n images, and in implementation, authors use n equals 2. Then from these n images, r proposals are sampled by sampling r by n proposals from each image. During sampling, we ensure that 25% of the proposals belong to some foreground class. The criteria for this is that their IOU is greater than 0.5 to some ground truth box. And the remaining ROIs are sampled from proposals with IOU greater than equal to 0.1 but less than 0.5 to any ground truth box. These are the proposals with ground truth labels as background class. This interval from 0.1 to 0.5 is a bit different from RCNN, wherein during classification fine-tuning, background proposals were those with IOU less than 0.5. So even those with overlap less than 0.1 were marked as background class proposals for training. Let's see this in more detail. Given this image and these two ground truth boxes, these are all the proposals with overlap greater than 0.5 to one of the ground truth boxes. And like in RCNN, if a proposal has greater than 0.5 overlap to both, then its ground truth assignment is the one with which the proposal has higher IOU. These are all less than 0.5 but greater than 0.1 overlap proposals. And these are those proposals with overlap less than 0.1. And here are some samples from each of these groups. In RCNN, we had seen that one of the reasons why SVM was giving better results than just classification fine-tuning was that for fine-tuning, these were the background class proposals. Because proposals with IOU less than 0.1 were also included, this meant that there were quite a large number of proposals which were easy to distinguish as background. SVM on the other hand was trained with hard negative mining and hence gave better results. In Fast-RCNN, we ignore all proposals with IOU less than 0.1. So intuitively, the easy to classify as background proposals. And instead train the network to classify only these 0.1 to 0.5 overlapping proposals as background. This allows the network to learn better discriminating features to distinguish between what is a person or car and what is just a part of a person or part of a car, and hence should be predicted as background. This 0.1 limit acts as a hard negative mining for Fast-RCNN. So instead of classification fine-tuning, SVM, and bounding box regressor, we just have one stage of training which takes these proposals generated from selective search and learns to classify them and better localize them using a single stage training but with multitask loss. And now let's get into the exact formulation of this multitask loss. The loss used by authors is a combination of classification and localization loss catering to both the layers, with hyperparameter lambda balancing between the two. and in implementation, lambda is just used as 1. Focusing on the classification loss, it's the cross entropy loss using the k+1 output probabilities from the classification layer and the ground truth class U for a given proposal. The localization part is just what RCNN had, but instead of using MSE, we use smooth L1 loss. Like we had seen, this will be between the 4 transformation parameters predicted by the network for this ground truth class U and the target transformation parameters. The identity function here ensures that the localization loss only kicks in for the non-background proposals, as the authors use the convention of background class being the 0th class. This is because only for the non-background proposals, we have a valid target transformation parameter to actually learn from. The last part of training, which we'll cover now, is what the authors do to have the network learn scale invariance. They experiment with 2 approaches. First, which they call brute force, is to simply resize all images to a fixed size before feeding to CNN and have the network learn scale invariance through training data itself. The second approach, which is multi-scale training, is where they make use of image pyramid and randomly select a pyramid scale for a given image during training. Both the approaches will also have differences in the way we inference. So remember, our model receives an input image and a list of proposals for that image. For the case of single scale testing or brute force, we extract regions proposals for a given image, resize this image to our predefined size, and feed it to the model to get classification and bounding box regression scores. And then finally filter predictions for each class separately using NMS. If you are not familiar with NMS, I provide its details in the RCNN video as well as in the MAP video. For the multi-scale testing, we still have those steps that we do in single scale, but there is an additional step of mapping the proposal box to a specific scale. We do this mapping such that the scaled ROI is closest to 2:4 x 2:4 in area. This 2:4 x 2:4 is the common size generally used during ImageNet training. So given this image and proposal, we first get the images at all pyramid scales. Then this ROI is extracted from each of those scales, so we will get 4 scaled ROIs. This proposal box is mapped to the scale for which the scaled ROI will be closest to 2:4 square in area. And ROI pooling for each proposal happens using the feature map and scale that is mapped to that proposal. So if this scaled ROI is closest to 2:4 square, then this corresponding image will be used to get this proposal's predictions. So you can see that rather than just doing one forward pass, we would be doing as many forward passes as there are scales in the pyramid, assuming every scale has at least one proposal mapped to it. Now let's summarize everything that has changed from RCNN. We first moved from forward passes for each proposal to a single forward pass for an image, and the proposal features are extracted using the ROI pooling layer. We got rid of SVM and the multi-stage training pipeline, and instead now have 2 branches of FC layers, one for classification and one for bounding box regression, trained using a multitask loss. And finally, we also added multi-scale approach using image pyramids along with brute force method to achieve scale invariance. Now let's see the results that we get with all of these changes in Fast-RCNN. The authors trained 3 variations of model: small, medium, and large, where large is the highest in terms of computational requirement and depth, and small is the lowest. Small model is just AlexNet. Medium is this VGG_CNN_M_1024 from another paper, which itself is just a variation of another architecture. And large one is the deep VGG16 model. Let's first start with the training time comparisons between RCNN and Fast-RCNN for all of these 3 variations. And these values are obtained from training on VOC 2007 dataset. RCNN for training takes 22, 28, and 84 hours on these 3 variations, whereas Fast-RCNN takes less than 2 hours for small and medium model and only 9.5 hours for the large model, which essentially means Fast-RCNN gives a speedup of 18.3 and 14x for small and medium, and 9x for the large versions. This speedup is all the more prominent when inference times are compared, where while RCNN takes roughly about 10 seconds per image for the small and medium models and 47 seconds for the large model, Fast-RCNN only takes less than 1 second for all variations, giving a speedup of almost 100x for the small and medium models and 150x for the large model. Moreover, these speedups do not come at any loss of accuracy of the model. For comparison of accuracy, only the large model was used, and remember, for RCNN using VGG16 on the VOC 2007 test set, we ended up getting 66 as the final MAP. Fast-RCNN also gets the same MAP, in fact a little bit higher only. And same for other variations of the dataset as well. Fast-RCNN always leads to a slight performance gain, and if we add more data during training, the MAP further improves. Next, we look at the impact of transitioning from multi-stage training of RCNN to single-stage multitask training in Fast-RCNN. To understand the benefits that this change gives us, if any, the authors first train a Fast-RCNN model only on classification loss, and we get the MAP values which are within the red box here. They also train a model on multitask loss, but no bounding box regression at test time. So the localization loss is indeed used during training, but the regression is not applied at test time. Now notice that for all the three variations, there is performance improvement. But the only difference was that rather than training just on classification, we also trained on localization. Since at test time the bounding box regression was not applied for both the cases, that means that this benefit only occurred because we trained the network to better localize the object as well as classify the object. Intuitively, forcing the network to capture features which better localize where exactly a car is ends up helping the network to better learn what exactly makes an object a car. So this explains the benefit of multitask loss. Now to compare single stage versus multi-stage RCNN approach, the authors take the classification model of first step and train only the bounding box regression layers. So this is like stage-wise approach of RCNN, where we first trained classification part and then trained the bounding box part. And this time we also add the bounding box regression at test time. This does improve the performance from all previous versions, but it's still lesser than what we get with Fast-RCNN using the single stage multitask training with bounding box regression added at test time, which asserts that the change from stage-wise training of RCNN to single stage training with multitask loss is indeed a contributing factor to the overall performance improvement. The last experiment that we will look is between single scale and multi-scale training, and the authors find that using multi-scale approach we get slightly higher MAP, but the change is not large enough, meaning that the network has learned scale invariance to some degree directly from the dataset itself without specifically training for it, which was the brute force approach. Also, this slightly higher MAP comes at a cost of increased compute time because of the forward passes for multiple scales. The authors, based on these results, stick to using only the single scale approach, where the image is resized to a predefined pixel size. This is because they feel single scale offers the best trade-off of speed versus accuracy. Now we are going to look into the final result, where the authors use SVD to further improve inference time. To understand why, let's look at the time consumed during conv layers and FC layers during inference of an image. These values will be for the VGG16 model, where the ROI pooling output is 7x7 with 512 channels. And if you flatten it, that means you have 25088 dimensional vector, and post that we have two FC layers, FC6, which is a 25088 x 4096 matrix, and FC7, which has a 4096 x 4096 weight matrix. And after that, obviously, we'll have the classification and bounding box FC layer. For the large model, we saw that the total inference time was 0.32 seconds. Out of this, the authors find that about 46% was spent on convolutional layers, and FC layers used about 45% of the inference time, and the remaining time is used by other layers like ROI pooling and so on. Hence, it would benefit if we somehow reduce the inference time for these FC layers, since about 45% of the total time is spent on them. For this, the authors take the weight matrix at the FC6 and FC7 layers. Then they apply SVD, but only select the first t singular values and vectors to get an approximate factorization of the weight vector. They then compress the FC6 and FC7 layers of the network by taking each FC layer or weight matrix, which say is of U cross V shape, and replacing it with two FC layers, one using the matrix U and the other using the diagonal matrix and V matrix. So what does this get us? The authors use t equals 1024 for the FC6 layer, which means that because of this factorization, rather than using one weight matrix of 25088 cross 4096, we are instead using a 25088 cross 1024 matrix and another matrix which is 1024 cross 4096. Which means we'll reduce the number of operations and time. Basically from U times V, we are now at TU plus TV. And if T is much smaller than U and V both, then this TU plus TV is of significantly lower value than UV. The same is also done for FC7, but with T being 256. Since we are now modifying the weight matrix, this leads to a performance drop. But if we compare the inference times, the conv layers still take the same time, but FC6 and FC7 inference times gets reduced to about 30% of their original value, which brings down the total inference time from 320 milliseconds to 220 milliseconds. And the performance drop is not that huge either. We drop from 66.9 to now getting a 66.6 MAP, so a 0.3 reduction. Here I did not get into details of SVD because that topic deserves a separate video in itself. So if you don't know about SVD, it's fine. As long as you understand ROI pooling and multitask loss, you should be good as far as the main components of Fast-RCNN is concerned. And this SVD is anyways not used in the next version of RCNN. Okay, so that now finishes everything that I had planned to cover in this Fast-RCNN video. From RCNN to Fast-RCNN, we introduced ROI pooling, saw everything that is happening inside that in detail, transition from multi-stage training pipeline to a simpler single-stage multitask training, and saw how the entire model is trained and what kind of results we get compared to RCNN. In the next video of this series, we'll move to faster RCNN. Hope you find this video helpful and thank you for watching it. See you in the next video.